I'd like to talk a little bit about what implicit differentiation is, how you go about using it, and when you would use it. So let's just start here. Basically, intuitively, informally, I guess I should say, implicit differentiation is a way of finding the derivative dy over dx when the equation specifying the relationship between x and y is not expressed in the form y equal to x. Maybe by contrast I can illustrate what I mean there. Up until now, before we started talking about implicit differentiation, when you were asked to take the derivative the one thing that all the exercises had in common and of course you can go on and on and on, is that you always had y equal to something. In other words, the equations were always solved for y. And our derivative rules made that assumption as well. But for implicit differentiation, I'll call it ID, situations where implicit differentiation would be appropriate. You might have an equation like x plus 3y squared equals 7, or maybe 4xy plus 4 is equal to 4, x over the square root of y minus 1 is equal to 0. And again, you could go on and on and on. But here's the contrast between the two things. Our old derivative rules up to now have assumed that you're going to have y equal to. Implicit differentiation shows us that we can actually find the derivative without having an explicit equation written in the form of y equal to something where it's a function of x. So even though we're going to think of y as being some function of x, we don't explicitly have to write it that way. So that's sort of what implicit differentiation is in a very simplistic way. Now I want to say something about how do you do it? How do you use implicit differentiation to find the derivative dy over dx? And it's basically a three-step process. Now right now I don't want you to get caught up in all the details, but basically understand the big picture idea. There are three basic steps. First, even though y is not explicitly written as a function of x, like the second column that I was showing you earlier of equations, you do make the assumption that y is some function of x. So if I went back to, say, the equation I wrote earlier, x plus 3y squared equals 7. Even without solving that for y, I'm going to assume that y is some function of x. So that's the first step. Make that assumption. That's very important. Once you make that assumption, and under that assumption, you take the derivative dy over dx of both sides of the equation term by term. So this particular equation, just to continue the example, if I take the derivative of both sides, I'm going to take the derivative of the first term, I'll take the derivative of the second term, and I'll take the derivative of the one term on the other side. Now again, I don't want to get too caught up in the details right now, but that's the process. Now, the derivative of x is just 1. The derivative of 3y squared, by the power rule, if you just think about it that way, is going to be 2 times 3 is 6, and then the y to the second drops down to y to the first. If that were an x, we'd be done. But remember the assumption number one. We're assuming that y is really some function of x. Now we're going to talk about this in more detail later, but for right now just try to keep an eye on the big picture. If y is really some function of x, then we have to come back by the chain rule and take the derivative of the base. And just as a slight aside, it's as if I were taking 2x to the 5th to the 3rd, and if that were the equation that I was trying to take the derivative of, then I would take the 3, bring it down and multiply it by the 1, and that'd give me 3. Then I'd write the base down, and I'd reduce the 3 to a 2. But then the chain rule would kick in, and the chain rule says since that's a function of x, I have to come back and multiply by the derivative of the base, which would be 10x. So that's the same sense that I'm thinking of y back here. Y is some function of x. So when I take 2 times 3 and get 6 and take the 2 down to a 1 and get just y to the first, I still have to come back and multiply by the derivative of y, which symbolically is dy over dx. And the derivative of a constant is always 0, so the right hand side would be 0. And the last step in the process is simplify this if you need to, and then solve for dy over dx. In other words, get this dy over dx on one side by itself. And that's easy enough because this problem is pretty simple. I just need to subtract 1 from both sides, and I would get 6y times dy over dx is equal to -1. And then if I divide both sides of that equation by 6y, I would get dy over dx is equal to -1 over 6y. So I don't want you to get bogged down in the details at this point. You'll have plenty more chances to actually look at the details. I want you to focus on the big picture, which is the 3-step process. Assume that y is a function of x. Under that assumption, take the derivative of every term on both sides of the equation, and then simplify and solve for dy over dx. That's the big picture. Don't sweat the details at this point. I do want to say this. Although the procedure itself is really simple to understand, and those 3 steps are really not that very difficult to understand, you've always got to be careful. And you've got to remember that whenever you take the derivative of a term, the assumption that y is a function of x means you have to treat the x, or whatever the independent variable is, differently than you treat y. Because y is really a function of x. It's not an independent variable. Let's look at an example just to sort of make that point. Suppose I have 3x plus y is equal to 5. According to our 3-step process, we need to take the derivative of each term. On both sides of the equation. Now I'm writing it out formally just sort of for emphasis. When you're doing this yourself, you may not even write down that particular step. But it does emphasize what I'm doing. Okay, the derivative of 3x is 3. The derivative of y with respect to x is what we're calling dy over dx. That's our symbol for it. And the derivative of any constant, in particular 5, is 0. And all we do now is take the 3 to the other side by subtracting 3 from both sides, and you get dy over dx is equal to -3. Simple example, but I think even from such a simple example, there are some lessons to be learned. And I want to emphasize that because that's a very important point here. And I want to do that by just taking some simple derivatives and trying to make my point. If I have just a constant, just say 5 like I had there earlier, its derivative is 0. Derivative of any constant is 0. If I have x, its derivative of course is 1. But if I have y, since y is treated as a function of x, the derivative of y is dy over dx, not 1. If I have something more complex involving just x, say 5x, that derivative would be 5. But if I had 5y, the derivative is going to be 5 times the derivative of y with respect to x. So when you have a constant 0, when you have some form, some term involving just x, it's your ordinary derivative rules, but whenever a y is involved, you're going to have a dy over dx. Suppose I had 3x plus y cubed equal to 5. Looks pretty similar, but it's more complex because the term involving y is more complex. But the procedure begins just the same. You take the derivative term by term. As before, the derivative of 3x is 3. But now y cubed will be 3y squared, but since y is a function of x, you've got to use the chain rule, which says come back and take the derivative of the base, which would be dy over dx. And then, of course, the derivative of 5, as we've said before, is 0. Now, you're still going to subtract a 3 from both sides. You're trying to isolate the dy over dx on one side by itself. In other words, solve for dy over dx. Now, if I divide both sides by 3y squared, I'll have dy over dx on one side by itself. And then you notice, of course, that the 3's will divide out, and you'll end up with dy over dx is equal to minus 1 over y squared. Now, I'm not sure there's really a different lesson to be learned here than the other example, but it is a good point, I guess, at which I can just say this, and that is, whenever you take the derivative of an expression involving y, it will always produce at least one dy over dx. When you're taking a term that only has x's in it, or a constant, you're not going to get any dy over dx's. But as soon as you come to a term, or a factor that's part of a term, or a quotient that has a y in it, somewhere in this process you're going to generate at least one dy over dx. You just have to remember that. And again, just for an example to look at for later, when I took the derivative of y cubed, I knew when I started I was going to have a dy over dx somewhere in the process. So you think about it and you say, well, the answer is just 3y squared. No, because I have to have a dy over dx somewhere in the answer, and that makes you think, okay, yeah, I remember now, I need to think of y as a function of x, which means the chain rule applies, which means I've got to come back now and take the derivative of the base, which is dy over dx. So be careful, think your way through these, and try to keep in mind these lessons that I pointed out. Another thing I would say and remind you of is that although implicit differentiation seems like a standalone topic, it's really not. It can involve any of the other rules you've already had for derivatives. I'm not necessarily listing them all of them, but the constant rule, the power rule, the product rule, the quotient rule, the chain rule, the rule for taking derivatives of exponents and logs, all those things are still in your toolbox, and they may be needed when you're doing implicit differentiation. And I'll do a couple of examples to illustrate that. I want to keep it simple, though. My point here is not to work hard, difficult, tricky problems, but to get you to see the big picture. There's more time for actual more difficult problems later. But here's the first example. X times y minus 5 equal to 0. If I want to take the derivative term by term, the first thing I'd notice, I suppose, is that x times y is a product. So that's going to involve me with the product rule. So I've got to take the derivative of that product. Now the product rule, I wrote it down here just to remind you. You take the first factor times the derivative of the second factor plus the second factor times the derivative of the first. So the first factor here is x. So you get x times the derivative of the second factor. Well, the derivative of y is dy over dx because it's a function of x, plus, then you reverse it, you take the second factor, the y, and multiply by the derivative of x, which is 1. So that's the product rule for the first term. Then you've got minus 5. Actually, you've got minus the derivative of 5 when you're writing the differential equation, and that would be 0. And of course, the derivative of 0 is 0. So if you're trying to solve this for dy over dx, those two terms are 0, so all you really have is x times dy over dx is equal to negative y, because that's y times 1 is y, and if I move it to the other side it becomes negative y. And then divide both sides by x, and I get dy over dx is equal to minus y over x. And I've done it. So the point here being, once you're doing implicit, any other derivative rule that you've had might come into play. I would now go and look at some actual problems that might be a little more difficult and see if you can apply what you've learned here.